Hello, thank you for watching. This is a pre-recorded version of my talk for OBase 2025 in Athens. Unfortunately, I won't be able to join the conference in person. I really appreciate the efforts made by the organizing committee to allow me to still give the talk remotely. Thank you, and let's get started. The title of my talk is Bayesian Smoothing and Feature Selection using Variational Automatic Relevance Determination. I know it is a long title, but I will unpack each part during the talk. This is a joint work with two of my students, Zach and Diptarka. They both were PhD students in the Department of Statistics at U of I and just graduated a month ago. Zach is now a machine learning engineer at Uber, and Diptarka is a financial analyst at Ernst Young. Here's a quick outline of the talk. I'll start with the motivation and background, and then walk you through our method and the computational algorithm. After that, I will present results from both real and simulated data to demonstrate that our approach is not only easy to use, but often outperform existing alternatives. For the introduction, we consider a classical regression problem. There are p features and a continuous response variable y. Our goal is to learn a function f that predicts y using a p-dimensional input. We all know the limitation of linear models, but at the same time, estimating a flexible, high-dimensional nonlinear function faces the curse of dimensionality. A nice trade-off between these two extremes was proposed by Hastie and Tibshirani, the additive model, where the regression function is represented as a sum of univariate functions. Each fj is a function of a single variable and xj, which can be either linear or nonlinear. This structure is clearly more flexible than a simple linear model, but it avoids the curse of dimensionality by keeping each component one-dimensional. When fitting an additive model, we usually have two goals. First, smoothing. We wanted to estimate each fj with appropriate level of smoothness. The second is feature selection. We wanted to identify and exclude fjs that are irrelevant to the prediction of y. So you may ask, why is it difficult to achieve those two goals simultaneously? Intuitively, this may not seem like a difficult task. After basis expansion, each fj becomes a linear combination of basis functions. So estimating fj reduces to estimating a vector of coefficients beta j. Given all the progress in variable selection and sparsity methods over the past few decades, it seems like we should be able to just apply those techniques directly to beta j, right? Well, here's a catch. Smoothing and feature selection are tightly coupled. Estimating fj isn't the same as doing ordinary linear regression. It's more like ridge regression, where each component comes with its own tuning parameter lambda j, which we often need to estimate adaptively. And this tuning parameter lambda j direct impacts the dimension of the corresponding ridge regression model. In ridge regression, the dimension of the model is typically defined as the trace of the smoother matrix, which depends on lambda j, and is usually not even an integer. The dimension becomes relevant when we use methods like group lasso or even a classical f-test. The dimension enters as a normalizing term either in the penalty function or in the f statistic. So here's a challenge. To decide whether fj should be included in the model, we need to know how smooth it is. That means we need to estimate its underlying smoothness parameter lambda j. But on the other hand, most existing variable selection algorithms rely on just a single global tuning parameter. They do not offer the flexibility to tune separate lambda j for each component. And this is precisely why many feature selection methods cannot be directly applied to additive models. Next, let me give a quick review on prior work for smoothing and feature selection in additive models. For smoothing, we typically use smoothing splines. The objective function aims to minimize the residual sum of squares plus a roughness penalty. Specifically, the penalty involves the integrated squared second derivative of each function fj. The intuition is that if a function fluctuates too much, its second derivative would be large in magnitude. And so the integrated squared term will be large, increasing the penalty and discouraging such behavior. Each fj has its own smoothing parameter lambda j, and a larger lambda results in a more smooth estimate of f, and a smaller lambda allows more flexibility. You can see this visually in the bottom panel of the curve plots. And there are two extremes. When lambda is 0, we do not penalize, and the estimated f essentially interpolates the data points. When lambda is equal to infinity, f is forced to be linear because linear function has 0 second derivative, and the penalty vanishes even lambda j is infinity. I will skip some of the mathematical details, but as covered in any standard course on smoothing splines, we will learn that to minimize this objective function, we need to represent fj using the natural cubic spline basis functions. Once we have the basis function representation, the objective function eventually reduces to a ridge regression with lambda j as a tuning parameter. Let me explain why we end up having a ridge type penalty. When f is represented as a linear combination of basis functions, its second derivative is also a linear combination of some functions, basically the second derivative of those basis functions. As a result, this squared term turns out to be a quadratic term in terms of the coefficient vector. Those integrals would involve just the basis functions and can be pre-computed. So ultimately, we get a ridge type penalty on the beta. Now, due to the smoothness of the ridge estimators, there are actually efficient ways to tune the smoothing parameter lambda j using criteria like GCV. And one state-of-the-art implementation in this R package MGCV, it automatically tunes lambda j inside the fitting algorithm. However, there's one major limitation. Smoothing splines do not induce exact sparsity. In other words, they do not perform feature selection. And let's take a look at some of the prior work for feature selection in additive models. One classical approach is stepwise selection. For example, in the aforementioned MGCV package, there is a function called step.gam that works similarly to stepwise regression for linear models. And this procedures works reasonably well for low-dimensional cases. However, it doesn't scale when the number of features p is large. Another family of methods is based on regularization. In this framework, we minimize a penalized residual sum of squares. The penalty term typically includes two components. One is a roughness penalty, and similar as a smoothing spline, that measures how wiggly f is. And the second is a sparsity-inducing term to encourage verbal selection. After basis expansion, the roughness penalty becomes a ridge type penalty on the coefficient beta j. For the second term, different papers may have a different form. Some may just directly measures the magnitude. Some has a little bit more complicated form, will include some kind of roughness in this J sub L and expression too. But eventually, it just corresponds to some kind of a group Lasso type penalty on the on beta J. So there are methods they do not have the group Lasso penalty component. For example, like smooth and spline. So there's no exact sparsity. And there are methods they do not have a ridge component. And for example, like SPAM, which we will see in the simulation study. Therefore, they don't have the ability to smooth each individual FJ. And some newer methods like a GAMCell include both components. However, they usually do not have an efficient way to learn those individual lambda j's in the ridge penalty. For example, GAMCell will pre-specify the smoothness penalty to some extent, and then choose only a single global regularization parameter lambda. Because in GAMCell, the J sub L also contains some smoothness penalty. So when lambda changes, and it also affects the individual smoothness. However, using a global tuning parameter for smoothness control is problematic when different FJs vary in smoothness. As we will see in our simulation study, GAMCell struggles when different FJs require very different level of smoothness. And there are also some Bayesian methods that have been proposed for smoothing and feature selection in additive models. And a common approach is to use a spike and slab prior as a function level for FJ. Of course, there will be additional layers of priors for the coefficients of FJ. After running MCMC, we can compute the posterior inclusion probability for each of the FJ and then decide whether FJ is 0 or not. This is a fully Bayesian treatment which has the advantage of carefully accounting for uncertainty at multiple levels, both in selection and smoothing. But the downside is that these methods tend to involve quite a few hyperparameters, and tuning becomes computationally expensive. Running a single MCMC chain may not be costly, but if we need to explore different hyperparameters, the cost quickly becomes very demanding. So let me summarize what we have learned from reviewing prior work. First, there's still no efficient method that jointly handles both smoothing and feature selection in additive models. Second, it is clear that we cannot avoid introducing a separate smoothing parameter lambda j for each fj. Learning those individual smoothing parameters is crucial, not just for estimation, but also for effective feature selection. So what are we going to propose? We will formulate the problem in a Bayesian regression setting. Specifically, we will decompose each function fj into a linear and a nonlinear component and place normal priors on the coefficients of each. The key is that we will use the variance parameter in those normal priors to control both smoothing and sparsity. It is well known that we can use the normal variance in the prior to control shrinkage and smoothness, but it is probably less known that we can also use those variances to induce sparsity. This idea is not new. Here I cite a classical reference, McCain 95. I'm not going to read the whole text here, but let me summarize the key ideas listed in those bullets. Suppose we have a model parameter theta and we believe the true parameter is sparse. Then one approach is to place a normal prior on each theta j and with its own variance Rj squared. Instead of fixing those variances ahead of time, we will learn them from the data. Now, here's a crucial point. If we choose Rj squared to be zero, then the prior becomes a point mass at zero, and the posterior for theta j collapses to zero as well. In other words, this just set theta j to be zero automatically. And this mechanism, known as automatic relevance determination (ARD), is the foundation of our approach. But our approach is slightly different from the prior work. In prior work on ARD, the variances are estimated by maximizing a marginal likelihood, similar to empirical Bayes. But as you're going to see in the later slides, we actually estimate them through a variational framework. And now let's formally introduce our method. Start with the matrix representation of the additive model. And given in training data points, we have a response vector of length n, and each feature vector is n by 1 vector denoted by this bold face xj. And we usually center the data, so we do not need to include the intercept in the model. We decompose each function fj into two parts, a linear component and a nonlinear component, represented using a set of basis functions. So this gives us a matrix representation of the model. The first p terms correspond to the nonlinear components, each represented by a design matrix Z formed from the basis function and a coefficient vector beta j. We allow a different number of basis functions for each feature, and so for Zj, it has D sub j columns. The next p terms correspond to the linear components. These are just single column xj and their corresponding scalar coefficients denoted by beta sub p plus j. And here for consistency, I use bold notation for all the betas, but the beta for the linear components is actually scalar. Now, this structure allows us to determine whether fj is zero, linear, or nonlinear based on the sparsity level of those betas. Now, we're going to specify what we called a group ARD prior. And this is just a straightforward extension of the original ARD idea. In the earlier work, the ARD prior is specified over a single parameter. But now in our case, because each component beta j could be multidimensional, so we're just going to place a shared prior variance over a set of coefficients. In short, this prior is just independent normal prior on each beta j with unknown prior variance Rj squared. This applies to both the nonlinear and the linear parts. So this prior variance Rj squares serves two purposes. One is a sparsity control, because when Rj is set to be zero, and it basically excludes the j's feature. It also serves as smoothness control, and when Rj is non-zero, and it corresponds to kind of regularization or penalty, and controls how wiggly the function estimated would be. And here I just use a slide to just elaborate those 2 points. And I mean, here the sparsity control is what we discussed before. This is the effect of an Rj set to be zero. Now, when Rj serves as a smoothing parameter, and how to understand this, it is a smoothness parameter, we can look at the minus log of the posterior distribution of beta. It has 3 terms: residual sum of square, and the 2 quadratic penalties on the linear and nonlinear coefficients. You're going to find out the first 2 we can match the first two terms with the objective function from the smoothness spline with our variance Rj squared reciprocally correspond to the smoothing parameter lambda j. So this is why in smoothness parameter, we want lambda j to be infinity, which is adding an infinite amount of penalty to force to suppress a nonlinear component. But in our setting, is correspond to setting the prior variance Rj squared to be 0. And to fit our model, we adopt a variational inference approach. And let me remind you the ingredients. We have the likelihood that depends on the regression coefficient beta j and the noise variance sigma square. Here I highlighted sigma square in blue on this slide just to emphasize that in our method, we actually do not need to estimate sigma square. I'll explain why shortly. We place independent normal priors only on beta j with error variance with unknown variance Rj squared as described before. We propose to approximate the true posterior with a variational distribution, which is also normal over beta j with its own variational mean mu j and the coherence matrix phi j. So all the parameters in red are what we need to estimate. We estimate them by minimizing the elbow. Elbow has two parts, the expected negative log likelihood averaged under the variational distribution Q, and the KL divergence between the variational distribution Q and the prior P. We also include a tuning parameter alpha tilde, which is a non-negative scalar that weights the two terms. Alpha tilde equal to 0 is basically the standard elbow used in the classical variational inference. And the idea of introducing a tunable weighting parameter has been explored before in other papers. In our case, it gives us additional flexibility during training, and this is actually the only hyperparameter of our algorithm. And we also wanted to mention out, if you expand the log likelihood term, you will notice that it involves sigma square. And so we have a something divided by sigma square here. So we can actually merge sigma square with alpha tilde and then introduce a new tuning parameter alpha in red. And so with this, we no longer need to estimate sigma square because it gets merged with the tuning parameter. And this will simplify the algorithm. Now, let's just take a moment to recap our setup and what we aim to optimize. We model response as a linear combination of those ZJs. We place independent normal prior on beta j with unknown variance and use a variational distribution with additional parameter on the mean and covariance matrices. So for each component at j, we need to estimate three quantities that are colored in red. The prior variance Rj squared, the variational mean mu j, and the variational coherence matrix phi j. So we do this by minimizing the elbow, and that depends on our tuning parameter alpha. And at first glance, this seems like we are making things unnecessarily difficult, as our variational formulation appears to triple the number of parameters. And naturally, you want to ask, is it still easy to learn? The answer is yes. As we will see in the algorithm, it turns out we only need to optimize Rj squared. The other two have closed form solutions once Rj is given. So now let's describe our algorithm. We optimize the elbow using a coordinate descent approach. At each step, we focus on just one block of parameters, those associated with component J, while holding all the other fixed. Then we cycle through all the 2p components and repeat until convergence. And here's how we update a single block. We rewrite the elbow into a simplified subproblem that only involves the parameter for the jth component. And again, it contains two parts. The first is expected negative log likelihood, and the second part is the KL divergence. And we want to point out that in the log likelihood, we are not working with original response vector y, but instead we work with the partial residual. So that basically represents what's the proportion in y that hasn't been explained by other components. When we evaluate the contribution of the other components, we basically estimate the unknown beta j by the variational mean mu. Now, the most important computational result is that one given Rj square, both mu and phi have closed form solution. I know I have so many mathematical expression on this slide, but no need to go through them line by line. I will just focus on explain the key ideas. And so once we plug in the expression of mu and phi into this objective function, then it reduces to a univariate problem with respect to r squared, and the objective function is denoted by g. Here I just want those symbols highlighted in red just indicate how to compute this function g and how this is related with the data. The function g is does not have a nice form, so the minimizer does not have a closed form expression. However, we can show that the minimizer must lies within a closed interval, and with lower bound divided by L, upper bound is divided by U. Here's how we give some expression of how we compute the L and U. Let's just go to the next page where we can have a visual. We can visually see the look of the function g. On this slide, we show 9 plots arranged in 3 columns. Each column represents one typical scenario for the function g. So let's start with the right column, which corresponds to this case. So this is a case where the lower actually happen pretty often. The lower and upper bounds are both 0. And remember the lower and upper bound, we basically calculate some numbers and take the positive part. So if all the numbers inside the parentheses is actually negative, then it just returns 0. So it is possible both the lower and upper bound are exactly 0. Then we know that the only valid value for r squared will be 0. So that tells us this component should be excluded. We achieve exact sparsity. And now let's look at the left column. Here, the lower bound is, both the lower bound and upper bound are positive. So we know r squared will be non-zero and this component will be relevant. And then we can use maybe grid search or some optimization to find out the optimal r squared. Now the middle column is the interesting case where the lower bound is 0 and the upper bound is positive. So in this middle case, we just have to be careful about the case represented in this picture, where we have a local minimum with non-zero r, but actually the global minimum is achieved by the boundary, which is r is 0. So the takeaway is that even though the function g doesn't take a very nice form, but it's well behaved and it's only one-dimensional, and with our bounding strategy, we only need to search over R in a closed interval. So that actually um, um, help the computation. Like we can just find the optimal R square very efficiently. So here's a summary of the full algorithm, and the input will be the response and the design matrix Z, which contains both nonlinear and linear components. So in total, 2p components, and a choice of the tuning parameter, and also some initial guess of the variational mean. And then we go through the loop. For each component J, we calculate the partial residual, and we calculate some function eta that will be used in this function G. The function G will also depends on this matrix called V, but you're going to find out the V will only depends on the Z. So we can always pre-compute these quantities and ahead of time. So once we find out what is the optimal choice of R squared, which is just a one-dimensional optimization problem, then we can update the variational mean mu and the covariance matrix phi. And then we do the update for all the 2p components and then iterate. Once we finish all this, then what's really useful is actually the variational mean mu, because that's the one we can use to replace the unknown coefficient beta. Next, let's talk about how we're going to choose alpha. Alpha plays a role similar to beta in lasso. So larger alpha will encourage a sparser model. We going to use cross-validation, and it can be shown that there's a natural maximum value for alpha, in the sense that when alpha is bigger than this, you're going to find out all the features will be excluded, because and as we discussed before, you're going to find out when alpha is too large, and we basically the lower bound and upper bound for all the R's will be just zero. So it basically for all the components, R squared will be zero and they are excluded. So we can find out a range. We can just specify a sequence of alpha values in this interval, and then we perform cross-validation for each alpha. The CV arrow look like a U-shaped curve, and then we're going to select the best alpha, either the one minimize the CV arrow, or something what we called standard error rule, which I'll explain using a real data set. So due to time constraint, I'm not going to go through the details for the Boston-Hudson data, but I do wanted to show this plot. When we apply our algorithm on this data set, we can produce this so-called CV plot. So the x-coordinate is denotes alpha in log scale, and the y-coordinate is a CV arrow, the mean square arrow, but it's actually a cross-validated mean square arrow. And depends on how many folds you use when you do the CV arrow. Suppose it's like 10-fold cross-validation. Then for every alpha, we're going to have a 10 CV arrows. So the red circle represents the mean CV arrow, and the gray vertical bar represent the one standard arrow around the mean. Similar to the GLMNet package for lasso, one can pick the optimal alpha by looking at the alpha give the smallest CV arrow. This is often denoted as alpha submean. Or you can pick a larger alpha. Its arrow is weighing one standard arrow of the around the alpha mean, and so this often called the one standard arrow rule for lasso. But in our study, we find out this one standard arrow doesn't work very well. Instead, we will recommend a 15% standard error and to pick a larger alpha. I have to admit 15% is a bit arbitrary, but we find out this procedure works very well in all of our simulation studies. Now, I want to use the remaining time to go over two simulation studies because that will show how our method differ from two other regularization algorithms. I'm just going to directly jump to this plot. So in this setting, we have a one-dimensional. It's a one-dimensional problem, and the true curve is a nonlinear has a nonlinear component. And so we compare SPAM, GAMCell, and our method. We produce, for every row, we produce the fitted curve in black, solid line, when the penalty is from small to large. So you can see the curve get pushed down when the penalty gets larger. And we wanted to focus on this SPAM plot. So for SPAM, as I mentioned earlier, in SPAM, it does not have a range type penalty. It actually just directly penalizes, to get sparsity, they just directly penalize the magnitude of the function fj. Now, because it cannot really, tune the smoothness of a function, you can see even when the penalty is very large, the fitted curve is still wiggly. Basically, have the same pattern and as the fitting when the penalty is small. And so this basically indicate that SPAM does not have the ability to perform smoothing, because if you look at the GAMCell and our approach, when the penalty is getting larger, so the smoothness level of the fitted curve actually change, not just to get smaller magnitude of the estimate. Now, in the next example, I wanted to compare GAMCell and our approach. This is a little bit more complicated case where we have 5 features. Now, x1, x2 are nonlinear, but apparently with very different smoothness level. x3 is linear, and x4 and x5 are actually irrelevant. As I mentioned before, GAMCell uses a single global parameter to tune the smoothness for all the features. So this approach will be problematic when those features have very different smoothness levels. I don't know if you can see the picture clearly, but in this case, clearly GAMCell doesn't do very well compared with our algorithm. For example, GAMCell didn't recognize x4 and x5 are actually irrelevant. It didn't give a linear fading for x3. And even for this two nonlinear fading, and it actually, if you get closer look, you're going to find out it misses the top part, this peak part. So this is just to confirm with our earlier comments about the drawback of GAMCell. So now I'm going to skip the remaining simulation study on feature selection accuracy and prediction accuracy. And I'm going to, due to the time constraint, I'm going to end my talk with this conclusion slide showing up here. This summarizes the key contribution of our work. Right now, our paper is under review for JCGS. Thank you for your attention. I think I'm going to pause here, and I'll come back to handle questions after Xenia finishes her discussion. Thank you.